Thank you, Lars. I'm here to tell you that there is alien technology and that you shouldn't be too worried about it, but it is every bit as mysterious as the phrase sounds. Now, I have to define what I mean by alien technology very carefully. So I do not mean I know it's cute, but I don't mean green visitors who come in their souped-up spacecraft or like that to visit our planet, even if they're friendly and well-meaning. What I do mean is something that you might say at first glance is a little more pedestrian. And I'll give you an example. The humble pine cone. I just picked one example out of probably millions of things around us that you think is an everyday object or everyday piece of your life. But in fact, if you really think about it, there's a degree of design here which has nothing to do with anything human. That these structures evolved eons before our ancestors evolved. And in fact, they're all around you if you only have eyes to see them. And this has given rise, I think, to, it's not an original thought, and it's given rise to a whole field called biomimetics, where people design technologies or architecture around the biological organism's solutions to different problems. In some cases, we don't even know what the quote-unquote problem is, but we do see the biological design around us. So I found this online. It's to me, it looks kind of alien, but in fact, it has basically the same architecture as the pine cone. If you look, you might know about the arrangements of the buds, the incipient buds on a pine cone called primordia. In fact, they form a kind of Fibonacci structure if you look at the spirals created. And in fact, that's what this architect was trying to capture in this pod building, right? It's always been my dream to live in a pod building. So I like this one. Now, the most striking examples of this are not at the level of pine cones and things that are macroscopic like us. It's actually the structures inside your cells. The structures inside your cells have nothing to do with any human design whatsoever. They're truly alien in the sense that we don't really understand them. And not only do we not understand them, we had nothing to do with them at all. If we go back to the most primitive cells, these structures go back billions of years. I think the latest estimate for bacterial origin is 4 billion years, something like that. And already a huge amount of structure and biochemistry was invented by bacteria, only refined by eukaryotes, which are our type of cell. Okay, so before I go any further, I'm going to show with the aid of some Hollywood special effects artists who actually work not far from where I used to live, near West Hartford. They were commissioned by Harvard University to work with some Harvard scientists, Harvard biologists, to create an animation. This was 10 years ago, but it's so spectacular I want to show it to you. And it comes with some music, too. Let's see if I can get it to play. Oops. And I stopped it. So just, oops, wait, sorry, that's not right. This is the right one, all right. We'll discuss afterward, okay, just going to let you view it. blue things, this is membrane, which will feature in my talk later. These are stiff filaments in the cell called the cytoskeleton. These are basically polymers formed out of proteins.
Louder, Greg.
Oh, yeah, sorry. Maybe I should turn this down. Another part of the cytoskeleton. This is an interesting cytoskeleton carrying a big membrane bag. This is all going on inside your cells. This is slowed down. Time scales here are milliseconds, but it's been slowed down so milliseconds become seconds, basically. This is a structure called a mitochondrion. Your cells have hundreds of those, maybe thousands. Again, membrane vesiculation, meaning membranes pinch off spheres. This is called the Golgi Apparatus. You may have heard of that. Now we're outside of a cell. The cell's rolling along other cells. And this rolling behavior, this is supposed to be a leukocyte. Leukocytes are your white blood cells. They're slipped out of the vasculature in between two other cells to fight an infection. Okay, that's what's going on in your body all the time, non-stop. If that's not alien technology, I don't know what it is. And so what does physics have to say about that? It's an interesting question. So first of all, when I saw this, I was very impressed that the tools of Hollywood were being applied to science. That was a great thing. But I was also concerned about some basic physics going on. First of all, even if you could have a camera that would be able to take pictures of all these things, of course, you can't have it using visible light because visible light's wavelength is just too big. It's bigger than almost all those structures. So, but let's put that aside. There's something missing here. It's the degree of crowding. You see these big vistas where there's nothing, and then you see the molecular machine off in the distance. That would all be filled with other stuff, all doing its thing simultaneously. And so you'd never be able to take a picture of it because you'd have to look through everything else. Of course, that doesn't make a very interesting movie. But the other thing is Brownian motion. You may know that at these scales, everything is in thermal motion. It's kind of a random jitter to everything. And whether that's important to the process depends on the energy scales involved in the processes, but it's there nonetheless in every one of those structures. So I think someone, it wasn't me, must have pointed these same things out to the filmmaker. So a few years later, they said, oh, we're going to fix it. We're going to put in crowding, and we're going to put in the random jitter. So let me show you what they did. I may have just played the same one over again. No, this is it. So now they try to fix it. Now they couldn't quite put in all the protein packing, but they did a lot better. Now they're zooming in on a neuron. You might know neurons have these extensions called dendrites, and they have a big fat part of their body called the soma. So now we're going through the soma, through an ion channel. Oh, okay. Now I hope there's no. Okay, it goes like this for 3 minutes. I can't take it. It's unwatchable. So there's a lesson there. Sometimes the schematics, like I'm going to show here, actually are better than if you had a movie of the real thing, quote unquote. None of that was the real thing, of course, but it's the best we could do with the scientific knowledge that we had 10 years ago, and then more recently, that one was made, I think, about 5 years ago. So let's go back to schematics, because the other one was giving me a headache and might have sparked an epileptic fit. I'm going to focus my talk not on the whole panoply of things that you saw in that movie, all those molecular machines. I'm going to focus on this thing that was recently discovered called Terasaki Ramps. And it's just a little reflection of the complexity that we see inside of cells that wasn't known. These Terasaki Ramps were just first published in 2013. So 4 years old. It's really quite new, and I think it's the tip of the iceberg in terms of looking at cellular structures. We're going to keep discovering new things that those filmmakers didn't know about because the scientists didn't know about them to tell them about it. So Terasaki ramps are a structure in something called the endoplasmic reticulum. I'm not going to say that word anymore. I'm just going to say ER because the biologists themselves avoid saying it. They just say ER for endoplasmic reticulum. It's something that's connected to the nucleus, which is here in purple, and it's indicated in this red kind of, I don't know what you'd call it, pinkish membrane structure. It's a membrane structure. It's very convoluted. Topologically, it's very complex. It's not very well characterized. In fact, I tried to work on it years ago, and I just gave up. I thought it's too complicated for physics. But that's where some progress was recently made, and that's what I'll describe. There's a lot of membrane structures in the cell. I mentioned the Golgi apparatus. There's other things called lysosomes, and there's peroxisomes. There's things that aren't even mentioned here. There's the nuclear envelope itself. And then there's the plasma membrane, what separates the outside of the cell from the inside of the cell. That's here. Those membranes all have the same architecture, exactly the same, and I'm going to tell you about it right now. It's a bilayer. It's really 2 molecules thick. The molecules are called phospholipids. Lipid is like fat, and phospho means there's a phosphorus atom in part of it, and I made a model here, which is hiding. Here's my own phospholipid I created. You can see in this model, black is carbon. Black is carbon. That makes sense. White is hydrogen. So these are called hydrocarbon chains. So the basic structure of a lipid, a phospholipid, is there's a phosphorus atom up in the head group. That's this purple thing. And then there's 2 hydrocarbon chains. These are oily chains. That is, from the thermodynamics point of view, they don't mix well with water. Water and the chains, they don't like each other. The chains would much rather be in an environment with other chains nearby and with no water, and the water would much rather be with other water molecules. So I'm kind of anthropomorphizing it, but all of that has to do with something called free energy in thermodynamics. It's a shorthand for talking about systems that have a huge number of microscopic states. And so it just happens that when you have these molecules in the conditions that you find inside of cells, that is pressure and temperature in a certain region, they like to form big sheets. And the sheets have this structure that, I'm going to pass this around. The sheets have the structure that the oily chains, to get away from the water, are all in a sandwich. They're the meat of the sandwich. And the bread of the sandwich are the head groups that contain the phosphorus. So these are called amphiphilic molecules because amphiphilic in Greek means they like both. That is, the head groups like water and the oily tails like themselves. But they're kind of welded together. So it's a funny arrangement where you can form this sandwich over gigantic scales compared to the scale of the molecule. The thickness here is only 5 nanometers. Okay, if you know what 5 nanometers means, it's 5 times 10 to the minus 9 meters. That's 5 over a billionth of a meter. Okay, it's very thin, but yet the scales at which it can extend can be thousands of times greater than that. So thousands of times greater than a nanometer is called a micron. That's only a millionth of a meter, okay? But in biology, that's a big difference, right? When you're in microns, you're beginning to measure the sizes of cells. When you're in tens of microns, 20 microns, 100 microns, you're measuring the sizes of some of our large cells. Okay, so I already described lipid molecules. I'm not going to go through it. This is my cartoon of a lipid bilayer. So these are my cartoon of the lipid. I'm just going to compress that to make it look like this. And this is the structure of what's called a sheet in an endoplasmic reticulum sheet. This is not just a bilayer. This is the bilayer, and this is a bilayer. But this is another fluid layer. And what's interesting about that is that this arrangement allows the cell to have shapes which aren't possible if you just had the bilayer. So for instance, as I said, the middle of the bilayer doesn't like water. If you break it, you would expose the meat of the sandwich to the water, and that thermodynamically is a big no-no. However, look, here I can have a kind of edge. Imagine this is a cross-section through a sheet that's going in and out of the board. This is a kind of edge, at least on a greater scale. It's curved in this cross-section, but it's coming in and out of the board. This is a way for the cell to have an edge to end the bilayer. So now it's not a bilayer, it's a bilayer plus another bilayer plus this layer. It's like a pentalayer because it's 5 layers thick. It's a way for the cell to have shapes that it couldn't have just with that. So in one sense, this added degree of complexity is necessary for the cell to make more complicated structures and more complicated machinery. So all I did in this case, that's not really a word, that's just lumen. I just reflected this about this mirror axis, or I rotated it like that. So this is, you could say, a figure of rotation, just a cross-section. So if you were to rotate this around, you'd see I have a wormhole now. A wormhole that connects this region with this region, and this is still separate from it. So it's funny, the cell seems to know about the topology of inside from out in a sense. But what do I mean by what's inside and out? This, for instance, could be the cytoplasm of a cell. That's where all the action you saw in that movie was happening. Over here, for instance, this could be inside the nucleus. Because this is exactly what you find in the nuclear envelope. The nuclear envelope isn't one of these. It's one of these doubled structures with its own lumen. So in fact, in this funny view, there's a topological, and by that I just mean things are connected to other things, between the cytoplasm and the nucleoplasm. So from the cell's point of view, the cytoplasm and the nucleoplasm are connected. The inside of the nucleus is connected to the stuff inside the cell. But it's disconnected from this thing called the lumen. Very interesting. Because that's the same space inside the endoplasmic reticulum also. So the cell keeps this topologically pure. It's kind of an invariant. It's very interesting. And you can see this in this schematic. I like this one because it shows 2 different shapes the endoplasmic reticulum can assume. One are the sheets, which look like flat layers that are parallel. And the other is a tubular network, which is much more complicated in this schematic. But what's in the pink region is that lumen I described. So the lumen here is connected to the lumen there, which is connected to the lumen there. It's all one continuous space. But I'm looking at it from the cytoplasm. So you can do things in the lumen that don't have to happen in the cytoplasm. It's a way for the cell to keep compartments separate. These are actual micrographs that I'm going to talk about in more depth. These were taken very recently, and the way to read this is down. You look at this, and then this, and this. Imagine slicing through a cell, physically slicing through a cell, and then doing an electron micrograph on each separate slice. That's what you see here. And what are you seeing? This is the endoplasmic reticular sheets caught in cross-section. And you can see there, you can see the lumen. The lumen is that little space between the 2 black lines there. So that's a bilayer, then the lumen, then the bilayer, and there's another sheet, and there's another sheet, and so on. It was this quality of data which allowed scientists, including I was part of that group, to understand how the sheets were connected to each other. Before this, it was actually a mystery how the sheets were connected, because no one could ever see a connection. They couldn't see tubes or any other structure actually connecting them. But they knew from biochemistry that you release something in the lumen of one, and it goes all over the lumen of the whole structure. So it was a mystery. Another mystery was why this more or less constant spacing between the sheets. Okay, I'm going to show actual data because I think it's really instructive. I'm going to show hundreds of micrographs, all in sequence. And I have to tell you, these are very thin slices. These are 30 nanometers thick. Imagine taking something and slicing it so it's only 30 billionth of a meter thick. You can't even see those slices because it's so far below the wavelength of light. So collecting something you can't see is really an art, and I'll describe a little bit about it. But I'm going to step through 120 of these. So this is the neuron of a mouse. This is a neuronal cell. And one thing you notice is there's a lot going on there. But in fact, you have no idea. This is just the membrane structures. All the proteins, all those filaments, all the small molecules, the DNA, none of that is being imaged here. This is a very particular technique that only stains membrane. So you're only looking at a fraction of what's going on. But you can see membrane is everywhere in this neuron. In fact, here's the Golgi apparatus. When you see this, you get a whole different appreciation for it. This is part of the same Golgi, but because you're slicing it, it looks disconnected. It actually is connected in a funny way. These are the endoplasmic reticular sheets that I was describing. And if you go through this, you can actually see, if you look at carefully, how sheets are connected to other sheets. And I'll just show you an example of it. It turns out to be topological, that word I used already, but I'm going to tell you what it means in this context. They're all over the place, but I just found one with my little eye. If I look here, this is a sheet. Here's a parallel sheet. Oops, and I don't know how to work the program. There we go. And what you'll see is there's a disconnection here. That edge, so that's the edge of a sheet, comes over to the other one, makes a junction, and then the opposite side disconnects. And now that one will bend to the next sheet, or no, actually, it did something a little more complicated in that case. But it bent to another sheet, and there was another disconnection, and so on. So this data revealed that there was something topologically really interesting about how sheets were connected to each other. By the way, I could talk for an hour on this one image. These are mitochondria. Those are those sausage-shaped things you saw in the movie. But here, of course, they just appear as ovals because you're slicing them. Turns out they're not just sausages. These are all connected to each other in kind of a network. So they don't have to be sausages, though they can be. Anyway.
I have a question.
Yeah, please.
Right over there.
Please ask questions, because
Is there a way to take those images, combine them into a 3D model?
Yeah.
So you could actually...
Yeah. I'm going to spend a lot of work doing that, and I can describe some of that, and I'll show some results of that. But I have to say, if you just do this to the whole structure, you get an unbelievable, complicated mess. You really have to focus in on these regions where you think something interesting is happening, and look only at those regions, and then find many examples of it. And I'll show the results of that. Any other questions? Yeah.
What is the imaging technique and how is it doing the thin slices?
I'll get to it. That's going to be a whole topic. All right. Okay, so let me go back to the presentation. I can figure that out. Okay. So I'm going to answer that right now, actually. How do we know what we know? Like, how do we know how to do that? What is that, So I'm going to start my story back in the 1930s. This guy, Ernst Ruska, he was a PhD student, and his advisor's name was Max Knoll, and they worked in Germany, so while the world was falling apart around them and things were terrible things, not unlike our own times, right? They were creating these incredible images because Ruska's thesis was he wanted to do for light, for photons, he wanted to do for electrons what had been done for light in microscopy. That is, he wanted a lens that could lens electrons. Of course, you need magnetic fields. But that was the overall idea. Can we use electrons, which have much smaller wavelengths, instead of photons? And this is one of their successful images. I think it was taken in the late 30s, but wasn't published until 1941. I love this image. It shows a bacterium. This is like an E. coli. It's about a micron across. And these are bacteriophages. These are viruses that attack bacteria. This might be the first image of a bacteriophage. So this is about a micron, but you can see this is pretty unresolved. It's not, you can't really tell what's going on with the bacterium. However, you can tell a lot about what's going on with the bacteriophage, and that's maybe, tens of nanometers, right, compared to this micron. So this technique was really good for things that were tens of nanometers, and less good for really big things, like microns. On zoom ahead to the 1950s, or late 40s, early 50s, Keith Porter, working at Rockefeller University, took these tools and really put them into the service of cell biology. That is, he made some of the pivotal breakthroughs that we're all relying on now. And one of them, in fact, they coined this word endoplasmic reticulum, which is marked already at that time ER. And this is a mitochondrion in the image. This is the nucleus. You see, the nucleus is big. You can't really tell what's going on with the nucleus. But if you look carefully, there's this gray structure, very lacy in the background. Let me zoom in. That was maybe the first image of the endoplasmic reticulum. This gigantic membrane structure everywhere, hiding out, kind of lacy in the background. Mitochondria, they're very dark because, again, they're staining for membrane. And membrane is very rich in mitochondria, it turns out. Very convoluted internal membrane structures there. This is what's called the Bloom-Porter microtome. The basic design is unchanged to this day. There's a very sharp blade, diamond blade or sapphire, and then the tissue is held there, and then this is repeatedly brought against the blade, and you physically slice the tissue as fine as you can. Blades are very expensive. They wear out very quickly, so that's a major expense. Let me show you the modern version. It's basically the same. Tissue holder, blade, you can't see it. This is a whole device to capture the slices. This is the real innovation. This was developed in Jeff Lichtman's lab. And by the way, I put a list of people who I should thank, but I won't have time to thank them. That's over there on the on the board. But Jeff Lichtman's lab at Harvard had this idea. What if we collect the slices that are coming off? Here's the tissue. There's the blade. They're coming off on this. What if we collect them on a rolling adhesive tape? This was a new idea. The rolling adhesive tape offers incredible advantages to the usual method. The usual method was a liquid film. Collect the slices on a liquid film. That has some advantages if you want to do cryo-electron work. But this has a great advantage because if it's rolling at a constant velocity and you're slicing at a constant velocity, you know in advance where every slice is going to fall. And you can put them in registry much easier this way than if you have something uncontrolled like a fluid, right? The big disadvantage here is if these slices are 30 nanometers thick, well, what's the thickness of an adhesive tape? It's like a human hair. It's like 100 microns or 60 microns at most. So what's the ratio between, if this is the slice, 30 nanometers, I would need 2,000 of those slices to equal the thickness of the adhesive tape. Big difference. That means you can't do transmission electron microscopy. The question was, what kind of microscopy are you doing? Well, the gold standard was always transmission electron microscopy. So what was Lichtman's solution? You do scanning. You do scattering off the surface. And you hope and pray that you're not missing too much in the next 30 nanometers. Because you're going to get that next slice for sure if everything works out. So you kind of cross your fingers. We're not going to miss too much by going to the next 30 nanometers. So we can just image on the surface of that slice. We don't care about the electrons going through it. That would be transmission. We're only looking at the backscatter, basically. Okay, so that's, like I described, that gave rise first to these images. These were done in mice neurons. Already there, so Terasaki saw something no one else saw in those images, and that was this first indication that there was this topological connection between the sheets. And so we first called it sheet-like endoplasmic reticular junctions. That didn't take off. But you can see it's not a tube at all. It's what I marked in blue here. So this is actually what you're asking about, three-dimensional reconstructions in a sense. What's blue here is the edge of the sheet. So it turns out the sheets are actually connected at their edges. But the edge is doing something funny. It's curving and it's twisting in space. Very interesting, because there are a couple things that curve and twist in space. I'm going to talk about it in a second. Here's a little movie of one of the first of these, I would say, Terasaki first junction, Terasaki Ramps as we call them now in biology. But I'll just run that again. All these edges are fake. The only edge that counts is the one in the middle there. It's only because I didn't have a lot of clay that I had these other edges. The only real edge is that thing winding through the center. It looks like that's what's connecting the sheets based on that data. So Terasaki had a great idea. He's an expert on ER and the nucleus. He said, why don't I take all those techniques, I move them to my lab, and we image all kinds of cells that are called secretory cells. Secretory cells are so called because they secrete. What are they secreting? Mostly proteins. Where are the proteins made? Turns out the endoplasmic reticulum. These cells have a job. Their job is to secrete molecules out of the cell. To do that, they need to have amazing endoplasmic reticulum. In the neurons, we were seeing like maybe 4 levels. In this, you can see 20, more, 30, something like that. It's a big difference. So I'm going to show you. So these are actual slices with that same technique. This is the endoplasmic reticulum. That's a mitochondrion sneaking in. I'm going to image in 3D what's going on in this right box, and then also what's happening in the left box. And I'll show that here. So that's the left box, and that's the right box, three-dimensional image, like you asked. It's a helix. In this case, it's a left-handed helix, and in this case, it's a right-handed helix. And in fact, when you look across the whole cell, across the whole ER, it turns out you seem to get 50% left-handed and 50% right-handed within the errors that we can. So there doesn't seem to be a fundamental helix in the sense of DNA, or what's called the alpha helix in proteins, which always comes in one-handedness. These seem to come in both chiralities, as we say in physics. So whatever's causing these can allow them to not break the symmetry, in a sense, in the physicist's language. So the symmetry doesn't seem to be broken. We get 50% left-handed, 50% right-handed. They're all over the structure. It actually allows you to think in a kind of physicist way now. You think, what about some of these mysteries about the structure? Well, is this the only way that sheets are connected to each other? It seems to be the only way that's really prominent in the data. It also explains why the sheets come in a kind of a wavelength. Why are they more or less equally spaced? Because that's what's called the pitch of a helix. So, I have something that's helical here. A helix, this is not quite a helix, this is something called a helicoid, but I'll get to it in a second. This has a periodicity in the z direction. And that's mapped onto the spacing between the sheets in a stack of sheets in the endoplasmic reticulum. So this ended up making a little bit of a splash in this journal called Cell. Physicists don't know about this journal, but biologists think it's really nifty. It made the cover, as you can see. This is one of those three-dimensional reconstructions. And the journal even commissioned this picture. and called it the parking garage model. In fact, they even put little cars on it. Just kidding. These are not cars. These are ribosomes, because it turns out, I haven't described it, but ribosomes are covering parts of the ER. Ribosomes are where the proteins are synthesized. So all the proteins that I showed you doing crazy things in the movie, they're all made somewhere. Where are they made? They're made in these machines called ribosomes. And that's what's coding parts of the ER. So the ER is enormously important. I didn't tell you how important it is, but it's a central thing. And some cell biologist named Sidney Tam decided to make a cartoon about this, because I think he liked that picture, and he actually made the ribosomes into cars entering a parking garage. And I think it's very funny. But in fact, it's not crazy. Parking garages are, the idea of a helical parking garage turns out goes back to the 1920s or so. I looked it up on this website. Oh, yeah, sorry.
Back in that cell cover.
Yeah, go back.
Yeah, which way is the nucleus and which way is the...
That's a good question. It doesn't matter. let me just say why. It may matter, but if you have, let's say, a right-handed helix, you turn it upside down, it's still a right-handed helix. So there's no way for me to tell which direction the nucleus was in. But
either up or down.
It's correct, yes. So you've identified an important thing. These sheets are locally flat, but when you look at the whole cell, that local direction seems to change depending on what part of the cell you're in. So you could always say, if I followed this long enough, I would hit the edge of the cell or I'd hit the nucleus. And that's absolutely right. Yes?
And these are breaking off from others and reconnecting to others?
The dynamics of these things is really interesting. We don't know, because when you do an electron micrograph, not only is the cell dead, the animal's dead, the tissue's dead. Everything has been changed to prepare it for these electrons, right? So the dynamics of these things is still a mystery. And so we need some new methods of observing very tiny things in cells. And these are coming on board in cell biology, but I don't think we know yet what the dynamics of these are. It's a great question. Okay. Yeah, please.
In that movie, you seem to show them connecting and breaking off.
Oh, yeah, so that's an interesting thing. That actually wasn't a movie. That was going through the Z direction as if it were a movie. That was a snapshot, a three-dimensional snapshot. But because my limitations, three-dimensional snapshots have to be processed in slices first, right? So that was a frozen structure that the electron micrograph was imaging, but it didn't represent time, right? But it could be exactly what you're saying, that there's a huge kind of complicated reconnection of helices. When you're talking about making a movie, now you have to imagine a helix is involved, not just the slices. So what's the helix doing in three-dimensional space plus time? It's a great question.
Great.
Yeah.
People may not understand that you keep taking slices in that helix, you'll see those breaks and coming back together.
Absolutely, yeah. So you take this funny helical structure. Well, let's go back to the data. Yeah, you take this funny helical structure and you slice it in any direction whatsoever, you're going to see those reconnections that you saw in the data. Okay, so what can physics do for this problem? To a physicist who studies soft condensed matter or even hard condensed matter, these structures seem very familiar. There's things called screw dislocations that you study in crystal planes. They're mathematically, they look very similar. So you might think the mathematics you can just import over. And basically that's correct. In soft matter, liquid crystals also have these defects. So in physics we use the word defect. It doesn't mean anything's wrong with it. It just means that there's a different kind of order, which isn't quite as perfect as it could be, but it's interesting and perfect in its own right in a different way. And that's what a defect means in physics. So I would call these topological defects in an otherwise parallel set of stacks. So there is an attractive model But to explain it, I have to go a little into what's called differential geometry of surfaces. So let me just make an attempt to do that. There is this thing called a helicoid. Here's a helicoid, which I'll pass around. And I've got another one here, which I'll pass around. This one's a little bigger. This one I got on Etsy. Supposed to hang it and let the wind rotate it and have deep thoughts. I'm going to make a helicoid here too. This is a business person's desk toy. There we go. Oops. Okay, so there's a helicoid also. You can get a helicoid very simply, almost too simply. You take a stick, like my pointer, you rotate it constantly at a constant rate while you also translate it in the z direction while you rotate it. That sweeps out a surface in three-dimensional space. That surface is called the helicoid. Now, what's special about the helicoid, it doesn't sound terribly complicated, but it has an interesting property. Its mean curvature is 0 everywhere. And what does that mean? That sounds complicated. So I'm going to give a lightning introduction to the geometry of surfaces and curvatures. Imagine I'm sitting at a surface, and I sit at a point, and I look in direction D1 and direction D2. I can fit a circle that best fits the curve, that's the intersection of that surface, in that direction, and I can fit another circle in the direction 90 degrees from that original direction. And so I'll have two different circles that are the best fits for those two directions. Those two circles have radii. Let's call it R1 and R2, okay? So I'm going to define a curvature in each of those two directions. C1 will be 1 over the radius 1, and C2 will be 1 over radius 2. So curvature in my language, I'm going to getting toward mean curvature, is always going to be 1 over length. There's another curvature that's called Gaussian curvature. I'll get to it in a second. So every curvature that I measure, no matter what direction, obviously has to lie between the minimum curvature and the maximum curvature. That's just a tautology. If there are a minimum and maximum, you could have a plane, for instance. Then it doesn't matter which direction you take. It's flat everywhere. So flat, I'm going to call this a circle of infinite radius, okay? So 1 over infinity is 0. So this has 0 curvature, this straight line. And in a plane, of course, no matter what direction you pick to choose, it's always going to be that line. So you're always going to get 0 curvature. So plane, I can tell you right off the top, the mean curvature, if I average, is always 0. But what about other shapes? Well, to look at all the other shapes, mathematicians realized, going back to Euler, this is before mathematics and physics split apart, so I don't know why I called him a mathematician. I should have called him a physicist. But Euler was, and Gauss also, were instrumental in using these curvatures to describe all surfaces, basically, all smooth surfaces. So the mean curvature is just the average of those two curvatures, and the Gaussian curvature is the product of those two curvatures. So I said this curvature had units of 1 over length. This curvature is a little different. It's got units of 1 over length squared. Okay, so that's the introduction. So now let's make a table. I already said a flat surface has 0 curvature and 0 curvature in the two directions. So therefore its mean is 0 and its product is 0. All right? Maybe I should stand over here sometime. A sphere, let me show you a sphere. Well, a sphere also has this property that it doesn't matter. So here's part of a sphere. I bought it today in Michael's. This time of year is great for buying different shapes at Michael's. It doesn't matter what point I pick on a sphere because all the points are equivalent, right? Let's just pick this one. If I measure what the maximum curvature is, well, it's going to be like that. Now I measure 90 degrees. Oops, this is harder than I thought. Hey, those circles are equal. They are the great circles. So I just get them equal. When I average, I get the same thing, and the product is just that. Okay, how about a cylinder? I'll skip the cylinder. I didn't bring it. Saddle. Okay, I've got something hyperbolic. Oh, it turns out the helicoid is the perfect hyperbolic surface for this. It's actually curved in a funny way. If you go across the region of even though I generated it from a straight line, it's actually highly curved. So if I go this way, the circle bends one way. If I go this way, the circle bends the other way. So I give those two different signs. One is going to be positive and one is negative. So it's quite possible, and in fact it's the case, that when you take the two curvatures, the principal curvatures for something like the helicoid, they add exactly to 0. And their product will be negative in that case. So if you hear the phrase, this is not an everyday phrase, but surfaces of negative Gaussian curvature, that's exactly what we're talking about here. All right? So you can go home tonight and say, oh, surfaces of negative Gaussian curvature, I got that covered. I know everything about that. So this is a surface of negative Gaussian curvature. And in fact, what's interesting, look at the surfaces that have 0 mean curvature. There's only 2 on this table. But there's plenty more, plenty. I got some examples here. You can come up afterward. This is a surface where every single point has 0 mean curvature. Exact cancellation at every single point. The only problem with this one is that if I were to extend it, it intersects itself. That's not very good for a biological model.
Oh, sorry.
Here's another one. This one you might know is called a catenoid. At every point of this surface, you get that exact cancellation also. And here's another one. It's called Enneper's surface, and so on and so forth. And here's another one, the helicoid that you're passing around. Now it turns out that this is actually goes back quite a ways why these surfaces are interesting for physics. And the first inkling, the first time it appeared in the literature, as it were, was back in the time of Sophie Germain. And Sophie Germain was interested in the elastic properties of lamina, which meant sheets. And she wrote a whole essay for a prize in Paris on this. She proposed that the energy should... A way to describe these surfaces is in terms of a kind of elastic energy. She proposed that it should have this form. I'm not going to go into great detail, but this is basically what we believe today with some slight refinements. The refinements are complicated, and I just flashed them here to show you how complicated they can get. But it's not really that different from what she said back in the early 1800s. Yeah, there's a question.
You can't leave that last slide without explaining why Bugs Bunny was...
Oh, yeah, it's a very interesting story. So she grew up, if you look, when she was in her teens, the French Revolution was happening. Paris was not a safe place to go out at night. Her parents said, you are staying home, and her father had an incredible library. He was a doctor. So she devoured every single book in his library, including all the math and physics books. She self-educated herself. And in fact, she started corresponding with all the greats of that era. Gauss, Laplace, Legendre, and so on and so forth. The only problem was she realized they wouldn't take her seriously because of her gender. Coming back to modern times, right? So she disguised herself as Monsieur Leblanc. Okay, so she would write all these letters discussing deep issues in mathematics and physics, but always as Monsieur Leblanc. Okay, so that was the time of Napoleonic wars and things, and France was invading Germany. She was a great fan of Gauss. She thought Gauss was the modern Archimedes. That's quite a statement, if you know who Archimedes was. She also read in her books how Archimedes died. Not a good story. He was too concerned with his geometric figures, and the Roman soldier who invaded his town said, listen to me, you're coming with me. He said, don't disturb my circles. Okay, that was it. That was the end of Archimedes. She didn't want that to happen to Gauss. So she was highly connected with people in the army, her father was, and they said, by all means, when you invade Braunschweig, where Gauss lived, take care of Mr. Gauss. Do not harm him. Treat him very nicely. So the general did exactly that. Sent a special contingent to Gauss's house. Said, hey, Herr Gauss, are you okay? Is everything okay? Do you need some Schnecken? Whatever. And in fact, that worked. Gauss was completely safe. And the general said, well, you have a great friend in Sophie Germain. And he goes, Sophie who? He'd never heard the name Sophie Germain because she was always Monsieur Leblanc. So Mel Blanc, Monsieur Leblanc, that's why. All right. So, okay, that's just my mental thing. Okay. All right. So, Sophie Germain basically was right on. You can make a kind of energy. You can make a kind of energy out of these geometric properties of curvatures. I'm not going to go into it, but I do want to note this is for a soap film situation, which is not exactly a membrane, but it's similar. And note, this equation, get rid of the constant, is just saying mean curvature equals 0. Mean curvature equals 0. It's amazing to me how much physicists and mathematicians can obsess on an equation like this and ponder it and get incredible insights. But all these surfaces I showed you are solutions of that equation. H equals 0. Every single point of these surfaces has mean curvature 0. And it turns out, if I went back a slide, this is a solution of all of those elastic equations. So if a membrane can take a shape in a cell, this is a possible description of the shapes it can take. And that's why it's very interesting to apply this gyroid, this is called a gyroid, to the Terasaki ramps. This makes an excellent model for a Terasaki ramp. All I have to do is take out the center of it. When I take out the center of it, I intersect that surface on a helix. So I have an infinite surface. This is not infinite, but that stick could keep going out. If I make it infinite and take out the center, I have an infinite surface that ends on a helix, and it's a minimal surface. So it's a solution of those elastic equations. So that's a huge advantage from the point of view of physics, because now I have a candidate that can describe those things. So what if I take a left-handed helicoid and a right-handed helicoid, prepared in this way of taking out the centers, and I bring them together? Can I make a surface that it's infinite, but it ends on two helices? And here's an example. So I'll pass this around. But this is a 3D printed mathematical model of a left-handed Terasaki ramp, or at least a model for one, and a right-handed one. And you can see the endoplasmic reticulum sheets, how they go off and become very, very flat. Okay. I'm going to show this image because it leads me to a slightly different topic, which is a little bit related to the question about dynamics. So this was made by my colleague Cemal Guven, who is an expert at working on these architectural CAD programs where you can make beautiful three-dimensional images. Our architects use these a lot, and also designers for machinery. But this is showing something interesting. You could split a left-handed and right-handed Terasaki ramp off of some other structure, and that structure looks almost like a three-way junction. A three-way junction, maybe in fact, one could have other kinds of geometries that aren't quite as simple as the thing I'm handing out by bringing different ramps together and different symmetries. So I call this origami, after the origami, of course. Oops, I'm getting ahead of myself. This opens up a new area, I think, which is, can you make designer-make structures and membranes that have the properties that are like the endoplasmic reticulum, but in fact, you get to choose where these Terasaki ramps are. And okay, so I want to make, in my last minutes here, I'm going to make a right angle and talk about an interesting connection that popped up in the last year, which is, can you find these ramps in nuclear astrophysics? And this takes on special urgency now that we've observed the merger of two neutron stars. I won't have anything to say about that directly in my talk, but maybe Lars has some speculations about that, because now I'm intruding in Lars's sandbox. So I noticed a certain article involving the work of a group at Indiana University, and so we started corresponding by email, sending each other images. Theirs from simulations of dense nuclear matter. And on my side, I was sending images that were electron micrographs from cells. And what we discovered was a commonality. So let me go a little bit into the nuclear astrophysics story. So in the mid-'80s, there were two famous papers. One of them is represented here by this Japanese group. The other was a group at Illinois, I think, Pethick, Wilson, and Ravenhall, or some permutation of that. They both were arguing an idea, and they made it a little more precise. The idea had been around since at least Hans Bethe's time, that when you have dense nuclear matter, nuclei are no longer, that is little spherical type things, are no longer the preferred shape that the collection of neutrons and protons wants to assume. In fact, as the matter gets denser, you move from something that looks like a nucleus, maybe it's a big one and a heavy one, but to something that could look more like a tube. And then when the tubes get dense and close together, it looks like a slab or a layer. And then when those get so dense, maybe you get an anti-tube. And then finally, maybe an anti-nucleus. That is, everything here is nuclear matter except for that empty spot. So this took on later the name nuclear pasta, because they called this nuclear spaghetti, nuclear lasagna. I don't know what they call this, but anyway, maybe nuclear gnocchi, and so on. Where do you find, it was already evident in those early papers, where you would find this state of matter. If you go through a neutron star, so as you know, a neutron star is what you get when you take neutrons and protons, any kind of matter actually, and smush it to a very high density. Basically, the protons and electrons will combine to make neutrons, and then you'll be left with some admixture of neutrons and protons with a sea of electrons around it. You go through a neutron star, that's about 10 kilometers in radius typically. Then, this is not to scale, but in the first kilometer or so, that's termed the crust, based on what we know about the nuclear state of matter for high densities. This is not very heavy compared to the rest of the star until you get in this little slice, which is about 100 meters before the end of that crust. Then this is called the core, and that's believed to be a fluid, a uniform fluid of nuclear matter. So this is kind of boring, and this is kind of boring out here because it's just a lattice of collection of nuclei. But what's really interesting is this dense structure in what's called the inner crust. Okay, so I've done a lot of damage to all the people studying neutron stars, but from my point of view, it's kind of boring, really interesting, right around here, okay? But note, this is 10 kilometers, and this interesting zone that I'm pointing out is only 100 meters. So it's 1% of, it's 1% because it's a tenth of a tenth, right? So it's a very thin region, but it's actually very massive compared to the rest of the crust here. Not compared to the star, but it's about maybe at least 40% or 50% of the mass of the crust, because the density's jumped up here by a factor of 1,000 or so. But that translates, it's not dense compared to this, but it translates into about 2 or 3% of the total mass of the neutron star. That's significant. Here's another artist's rendition. The nuclei are beginning to get closer. They're interesting. They're getting bigger. Spaghetti, lasagna, then the antiphases. So here's a simulation from that Indiana group. Let's see if I can run this. This is actually a simulation of dense nuclear matter done in a certain way that I don't have time to describe. But the way they do it is they make the box bigger and bigger slowly. So that's decreasing the density. So imagine this is nuclear matter going out from the edge of the crust out from the inner edge to the outer edge. Something interesting happens right when these lasagna sheets, you missed it right there. Oh, there it is. Oh, okay, right there. All right. The lasagna sheets were kind of parallel, and then all of a sudden they developed all these connections. What are the connections between those layers? Is it like the Terasaki Ramps? It turns out, so this is just snapshots of what I showed you. This is from a cell. This is from the nuclear data. It's an exact correspondence. The same geometrical structure is found down inside our cells, and also, presumably, in the crust of neutron stars. Nuclear matter, compared to our matter, it's more exotic because we don't live there. But in a sense, the equations are simpler because it's just neutrons and protons. It's in a sense, there's a way in which there has to be something like this in the crust of neutron stars because we know the density changes. So we know that there's a zone there where you're in a sweet spot. You can't avoid it. Okay, so here's some snapshots showing, in fact, very detailed pictures zooming in on the left-handed and right-handed Terasaki ramps, and they form arrays. So like I was saying, origami, you might have 2 come together or 4 come together. They're finding entire streets of left-handed and right-handed. So you could take a little box around here and say it goes left, right, left, right, left, right. So the basic unit is what's called a quadrupole in physics because it has 4 of these defects. But for theoretical reasons, we believe this is maybe the unit in which these things are organized. But okay, I want to end on this last. I'm almost good. I want to end on this very last speculation. There was a book by Robert Forward many years ago, which was about very speculative science fiction, of course, about life on the surface of a neutron star. Now, on a neutron star, you have to know the scales are so different. It's incredibly dense, and length scales are measured in tens of femtometers. That's 10 to the minus 14 meters. Time is measured in femtoseconds. So you could have entire civilizations come and go in the blink of an eye on the surface of a neutron star. What Forward thought was, maybe on the crust of a neutron star there'd be some interesting things going on. He called it nuclear chemistry. Well, that means something else completely to nuclear physicists. Nuclear chemistry is not what's going on in the crust of a neutron star, but what if he knew about nuclear pasta? He didn't really know about nuclear pasta. That's where the most interesting shapes are. That's where all that activity was happening. Could it be that activity could support complicated structures kind of analogous to what we have on the Earth? It's complete speculation, but I think it's a funny thing to think about because that zone, for sure, in my point of view, has the most interesting structure. Okay, so I'm going to end my talk there. You can read these. I don't have to read them. But it looks like the cell, with its complicated technology, really uses some basic physics to construct the things it has there. That is, yes, they're complicated, but in fact, there's fundamental physical laws underlying, at least the one I've focused on in this talk. And not only does it take place in the cell, we might also find that physical law isn't restricted to things that are made of lipid molecules and water and things like that. But in fact, that same motif may appear in other forms of matter. The physics is very different in its fundamentals, but maybe at a larger scale, there's a common description of these two phenomena. Thank you. Yeah.
Would it be valid to reverse the sense of that last statement there? What was the question? Wouldn't it be valid to reverse the sense of that last statement, that the geometry results from the energy?
It's absolutely true. that the geometry does result from the detailed equations, right? But I've reversed it to make a point here, and that's that the geometry is so amazingly similar. Does this give us a new way to think about, let's say, one or the other of the systems? So in nuclear physics, they use something called the semi-empirical mass formula. The ideas I showed involving curvature, they're nowhere to be found in that subject. So the nuclear physicists are very interested in this connection because it may give them a new way to make effective theories. Effective theories are very useful in physics because often you can't solve the quantum mechanical problem exactly. You need to step back and smear things out a bit. And that smearing out may give you different equations. And one question is do those equations have anything to do with the equations in the biophysics? And that's something being worked on now. So.
Yeah. So, going back many years, the algebraic topological structures, are they maintained through these transformations, or do they actually have different Betty numbers?
Okay, so I'll just translate your question for everyone. A Betty number is a way to talk about the connectivity of a surface and the kind of holes it can have, basically. You can combine the Betty numbers in something called the Euler Characteristic. Back to Euler again. So the Euler Characteristic is what tells you the difference between something like this and a sphere. Like this has a hole, but the surface of a sphere doesn't. So the question is, are these topological invariants actually invariant in the biological system? And to first order, I'd say yes, but we don't. But there are examples where proteins, specialized proteins embedded in membranes, can actually change the topology. So you saw that that was pictured in the animation when you had a sheet which represented the endoplasmic reticular sheet, and then all of a sudden a little sphere budded up out of that, like a little disc, something like this. And then it detached. That's a topological change. And that's created, not usually naturally, but through the agency of proteins. So proteins, which are burning ATPs, the energy unit in cells, they can actually change the topology of membranes. So I'd say we don't know precisely if the Terasaki ramps work in that particular way with machines changing topologies. But if left on their own devices, topology would be invariant, yeah.
You know, at the start, you showed the membrane.
Yes.
One layer here, one layer here. It is like a capacitor.
Mm-hmm. Yeah.
And that means it can store information.
Yep.
And that means that depending on the frequency that you apply, the capacitance changes. See what I mean?
Yeah.
It might be 100 hertz, one capacitant.
Yeah.
Gigahertz or megahertz.
Right.
Like the phone that we use, for example, in here. So the frequency changes. And I try to, connect to the cancer that I had in my ear because of the use of cell phone.
Yep.
Effectively, when the cell phone is used, it is providing a sinusoidal signal.
Yep.
And you have a layer here, which is a capacitor.
Yep.
Effectively, that layer cannot rapidly pass the nutrient to the cell.
Okay. Well, let me make a comment. I think it's actually interesting what you're proposing. So these layers that are parallel, they don't carry net charge. That's not. They may have a slight charge, but it's screened by the aqueous environment around them. So there's a screening length which is quite short. So that doesn't mean that there's no electrostatic interactions between neighboring sheets. It just means it's highly reduced from what you would expect naively. Now, the frequencies you're talking about they would actually be observable in cells. So in fact, one could test your hypothesis that these radio frequencies or other frequencies would actually oscillate the layers of the endoplasmic reticulum. I haven't seen any literature on that, but it's not absolutely crazy. And in fact, it's known that cancer often is associated with weird membrane structures. So I don't know the answer off the top, but I think it's not unreasonable to think there could be some connection there.
All right, I think we should thank Greg.
Okay.